This video discusses the nanoparticle synthesis methods that have been used. This module focuses on the top-down and bottom-up synthesis methods to make metal and semiconductor nanoparticles. If you enjoy watching this video, please click like, subscribe, and share so that you can be notified of new videos that I post in this channel. The two major types of nanoparticle synthesis methods are top-down methods and bottom-up methods. A few examples of top-down methods include mechanical milling, which is also referred to as ball milling, the process of laser ablation, and different lithography methods such as photolithography and electron beam lithography. In the case of bottom-up methods, the most common methods are chemical reduction methods and sol-gel synthesis methods. I will be discussing different chemical reduction methods, such as hydrogen reduction method, sodium borohydride reduction method, citrate reduction method, ethanol reduction method, and polyol reduction method. In the case of a sol-gel method, I will discuss the Stober synthesis method. I will now start by discussing the three types of top-down synthesis methods, which are mechanical milling, ball milling, laser ablation, and lithography techniques, such as photolithography and electron beam lithography. Mechanical milling, which is also known as ball milling, is a top-down synthesis method since it involves crushing and grinding bulk materials by using high-energy ball mills. This method can be used to prepare a variety of metal, metal oxide, and ceramic nanoparticles. A major advantage of this method is that the process is scalable, which means it could be useful for industrial processes and also uses simple equipment, which can also make it convenient. However, there are some limitations, such as that the nanoparticles that are formed are not monodisperse and has a large variation in sizes. This is very unattractive for a variety of applications. Also, another major disadvantage is that considerable contamination from the ball milling media could occur, resulting in impure contaminated nanoparticles being formed, which is also unattractive. These limitations would ultimately make the scalability advantage of this method not as feasible for different applications. Another top-down method involves the process of laser ablation, and this method involves directing a high-energy laser pulse to a bulk material which has been submerged in a liquid or a gas. This process causes vaporizing of the material to form nanoparticles. This method is used for the synthesis of metal nanoparticles such as gold, silver, and platinum nanoparticles. It can also be used to synthesize semiconductor nanoparticles and different types of carbon-based nanomaterials. One advantage of this method is that the process that is used results in high-purity nanoparticles. Another advantage is that the process does not require the use of any chemicals. However, there are some limitations, such as the fact that this process is an expensive one and results in very low yield of the nanoparticles. This is not good for applications requiring scaling up and also not useful for industrial processes. Also, it requires precise control, which might be difficult. The third type of top-down synthesis method are lithography techniques such as photolithography or electron beam lithography. Both methods are advanced fabrication techniques. Both of these methods have been used for the synthesis of metal and semiconductor nanoparticles. Advantages to using these methods are that there is high precision and it is possible to control the shape of the nanoparticles that are formed. However, lithography processes are generally very complex, expensive, and as a result is not useful or practical for large-scale synthetic processes. Photolithography is used in the production of integrated circuits and memory chips. Electron beam lithography is used for nanoscale patterning of metals, semiconductors, and dielectrics. We will now discuss 5 types of chemical reduction methods and also a sol-gel method, and all of these are bottom-up methods of synthesizing nanoparticles. The hydrogen reduction method is used to make platinum, palladium, rhodium, and their bimetallic nanoparticles of different shapes. The shape that is acquired is dependent on the specific type of polymer that is used. In the case of preparing tetrahedral platinum nanoparticles, the point+2 or point+4 salt, potassium tetrachloroplatinate or potassium hexachloroplatinate salt is added to doubly deionized water, and PVP of molecular weight 360,000 is used as the stabilizer. After the solution is prepared, argon gas is first bubbled using a gas trap for 15 minutes. Next, hydrogen gas is bubbled for 5 minutes. This process results in the formation of tetrahedral platinum nanoparticles. The gas trap is sealed and the hydrogen gas is allowed to react overnight to form the nanoparticles. In the case of production of cubic platinum nanoparticles, polyacrylate is used as the polymeric capping agent. After adding potassium tetrachloroplatinate or potassium hexachloroplatinate and polyacrylate to the doubly deionized water, argon is bubbled for 15 minutes, and then hydrogen gas is bubbled for 5 minutes. This results in the formation of cubic platinum nanoparticles. The sealed flask was allowed to react with the hydrogen overnight to form the cubic nanoparticles. Both of these nanoparticles are light brown in color. Another chemical reduction method is the sodium borohydride reduction method. This method is a very fast reduction method and involves using sodium citrate as the capping agent and sodium borohydride as the reducing agent, and a 0.2 or 0.4 salt can be used. The sodium borohydride solution is kept in an ice bath, and ice-cold sodium borohydride is added to the solution containing the sodium citrate and metal salt. The scintillation vial needs to be shaken vigorously while periodically opening the cap to release the evolved hydrogen gas. This synthesis method typically results in very small spherical nanoparticles and can be used for all the noble and transition metal nanoparticles. Other capping agents can also be used to prepare the nanoparticles, such as cetyl-trimethylammonium bromide. This method results in the formation of very small nanoparticles between 2 to 3 nanometers, and the nanoparticles are brown in color. The citrate reduction method was discovered by John Turkovich and his colleagues, and then later on was refined by friends to obtain higher monodispersity of the nanoparticles that are formed. In this method, sodium citrate is used as both the reducing agent and the stabilizer, and chloroworic acid is used as the gold precursor source. The polyol synthesis method involves the use of a polyol such as ethylene glycol and PVP as the capping agent. The ethylene glycol is the reducing agent as well as solvent, and a metal acetate or metal nitrate is used as the precursor metal salt. The reaction proceeds at high temperatures and occurs when the ethylene glycol refluxes. This method has been used to make silver, gold, and palladium nanoparticles of different shapes. The ethanol reduction method is used for synthesis of small spherical palladium or platinum nanoparticles, as well as other transition metal nanoparticles. In this method, PVP, molecular weight of 40,000, is added to doubly deionized water. When the solution begins to reflux, ethanol is added as the reducing agent, and this results in a dark brown nanoparticle solution being formed. There have been many recent reports on the development of green or eco-friendly synthetic methods, since there are environmental concerns about the possible toxicity of nanoparticles. In these eco-friendly processes, some examples of reducing agents include plant extract, bacteria, fungi, or enzymes. These methods are commonly used for the synthesis of gold, silver, and zinc oxide nanoparticles. Sol-gel methods typically involve the synthesis of metal oxide nanoparticles such as silicon dioxide, titanium dioxide, or zinc oxide nanoparticles. It involves the hydrolysis and condensation of the metal alkoxides or salts. The entire process results in the formation of the nanoparticles in a gel matrix. A very well-known sol-gel method for synthesizing silicon dioxide colloids is the Stober synthesis method, which we will discuss in the next slide. The Stober synthesis method involves the addition of tetraethyl orthosilicate to doubly deionized water, and then ammonium hydroxide is added to catalyze hydrolysis/condensation, in which the silica colloids which are formed are white in color. A similar type of hydrolysis and condensation process can be conducted to form titania colloids by using the titanium-based alkoxides with the hydrolysis and condensation process. To sum up this video on nanoparticle synthesis methods, there are two major ways to make nanoparticles, which are using the top-down method or the bottom-up method. Some examples of top-down methods include mechanical milling/ball milling, laser ablation, photolithography, and electron beam lithography. Some examples of bottom-up methods include chemical reduction methods and sol-gel methods. Chemical reduction methods include the polyol method, the citrate reduction method, the sodium borohydride reduction method, the hydrogen reduction method, and the ethanol reduction method. The most famous sol-gel method is the Stober synthetic method. If you enjoyed watching this video, Please click like, subscribe, and share so you will be notified of new videos that I post in this channel.